This is Liam in for Bear. Why do statisticians say sum of squares? Show me buy-in style. The most used tool in statistics for asking do these groups really differ is secretly the oldest theorem in geometry. We're going to watch a small dataset build the Pythagorean theorem and then see two famous results, ANOVA and the bias-variance trade-off, fall out of one picture. Three groups, 5 values each, 15 points. The black line is the grand mean, the average of all 15 values together, which is 7. The groups don't overlap. The question is how much they differ and how to measure it honestly. Pick the top right point, value 12, farthest from the grand mean of 7. Its total deviation is the yellow segment, 12 minus 7, 5 units of distance. That yellow segment is the raw material. We're going to square it and do it 15 times. Watch it split. The yellow segment breaks into two pieces. The blue piece, the group mean minus the grand mean, measures where the group sits relative to the whole. The red piece, the value minus the group mean, measures scatter inside the group. Blue plus red equals yellow always. Do it for all 15 points. Now square them. Every yellow deviation becomes a yellow square. They pour into a single yellow square of area 136. Every blue piece into a single blue square of area 130. Every red piece into a single red square of area 6. 130 plus 6 equals 136. SSD equals SSB plus SSW. Why? The claim in Byrne's idiom, the yellow square equals the blue square plus the red square. 136 equals 130 plus 6. 3 colored areas, 1 equation. The right angle hasn't been earned yet. Here's the honest hard beat. Squaring a sum gives 3 terms, not 2. Blue squared, red squared, and 2 times blue times red. For the whole equation to hold, those cross terms must cancel. Watch for each group the red deviations, how each point sits above or below its group mean, sum to exactly 0. They cancel. The groups enforce it. That 0 is the right angle earned, not assumed. Square root of 130, the blue leg. Square root of 6, the red leg. Right angle between them verified. Square root of 136, the yellow hypotenuse. 3 squares bloom on their sides. Euclid I, 47, built from your data. ANOVA asks one question using this triangle. How big is the blue square compared to the red square? Divide each by its degrees of freedom, 2 for between groups, 12 for within, and you get the F statistic. Here, 65 divided by 0.5, F equals 130. The blue square dwarfs the red. The groups really differ. New dataset, same triangle. 12 model predictions of one true target, value 10. These dots don't scatter around 10, they cluster around 14. The model is consistently wrong in the same direction. The blue segment is the bias. The mean prediction misses truth by 4 units. Relabel, blue leg, the bias, how far the mean prediction sits from truth, 4 units. Red leg, the standard deviation of predictions around their own mean, 2 units. Yellow hypotenuse, total error. Blue squared plus red squared equals yellow squared. 16 plus 4 equals 20. MSE equals bias squared plus variance. The trade-off, make the model more flexible. The blue leg shrinks, the red leg grows. The hypotenuse barely moves. Make it rigid, the red shrinks, the blue grows. The sum of the squares is conserved, not the individual squares. That is a design constraint. 2 triangles, same hypotenuse. The picture is the argument. 1 right triangle, 3 theorems, Euclid I, 47 ANOVA, bias-variance, sum of squares was never a metaphor. Your prompt has 2 jobs. It makes Claude verify the arithmetic before drawing anything. SSB plus SSW must equal SSD exactly, and it ends with a question, not an answer. What does the F-test formalize is the next thread. The triangle shows you the picture, the test names the probability. Run this on your own data and watch whether your blue square dwarfs the red. Take this prompt, paste it into Claude, and run it. The statisticians, Pythagoras, Liam in for Bear.